In section 34, we're analyzing the graphs of exponential functions. We're looking for things like y-intercept, x-intercept, zeros, and also if the graph is increasing or decreasing, and some quick ways to be able to figure that information out quickly. So the first activity we did was a card sort activity. So we had available to us, we had graphs, 12 of them, that we were trying to figure out, all right, which ones have positive y-intercepts, negative y-intercepts, or another. So we looked at the graph, and again, a y-intercept, just like we did with linear functions, no different here, is where the graph is going to cross the y-axis. So on graph A, we can see that that's a positive y-intercept at positive 1. Graph B has a positive y-intercept of 4. Same with graph C. Graph D would have a negative y-intercept, maybe about negative 1.5 or so. Graph E would have a y-intercept of 0, so we would classify that as other because it's neither positive nor negative. Graph F would have a positive y-intercept, somewhere in the 4 to 5 range. Graph G is a positive y-intercept between 1 and 2. And graph H is one of those that's kind of challenging for us because we don't actually see where the graph crosses the y-axis. However, we have reason to believe that the graph will continue along its trend and continue on that slope and eventually will cross the y-axis. And based on the graph that we see there, it's going to be in the on the positive y-axis. So we have a positive y-intercept for that. Graph I would be a negative y-intercept of negative 2. Same with J. K has a negative y-intercept somewhere between negative 3 and negative 4. And again, graph L is one of those that we don't see where the y-intercept is, but if we assume that it continues that trend, we can find out where that actually is. We're going to find out later that in order to find the y-intercept of the graph, there's a quick way to do it. If you're really unsure, you can just plug a certain number in, and that'll get you there. In round 2, we're looking for x-intercepts, and we want to know which one had a positive x-intercept, a negative x-intercept, or other. So on graph A, and believe it or not, I think this is the most challenging one because it appears that the graph does equal 0 at some point because this graph is kind of going down, very, very, very close to 0. But our definition of an x-intercept is where the graph crosses the x-axis. Well, based on that, I don't really see a place where it's going to cross over into the negative region. Unlike with the graph of y, where we assumed it was going to grow, the slope will get bigger when we have an exponential function that's growing. But when we get to this far left-hand side, that height is getting smaller and smaller. We can't take 2 to any power and get 0 or even a negative number. So we're going to say that this particular graph never crosses the x-axis. We know on B that's the same thing because we've got this little dotted line here that kind of sets up a little boundary, and we'll talk about what that is in a few minutes. Same with C. That same boundary. Graph D does cross here around 2, crosses the x-axis, so that's a positive x-intercept. Graph E crosses at 0, so that would be classified as other. Graph F is at about 3/4 approximately. Again, we don't know for sure that it is, but we know it's somewhere between 0 and 1. So that's a positive value. And G does not cross the x-axis, nor does H. I will cross at positive 1, and J will cross at negative 1. Here's the cool part about that activity. Once we ask you about the x-intercept, we ask you about zeros. If you remember all the way back to section 14, I know that was a long time ago, there is a direct relationship between the x-intercepts and the zeros, and that is they're the same thing. So again, it's just a different way for us to ask you the same question, looking for the same quantity. Sometimes those quantities are also called roots, so just be on the lookout for that in future classes. And then the last thing we're asked to do is find for increasing or decreasing. Now, this one should be pretty straightforward. We're just looking, does the graph rise or fall as we move from left to right? Graph A would be an increase, as would B. C would be a decrease, dropping in value. D is an increase. E would be a decrease, as would F. And G. H and I are both increases as they're moving up as we go from left to right. Again, it's always from left to right, so keep that in mind. And J and K would be decreases, and L would be an increase. So it'd be really nice if we could just find a way that if we just had an equation, we could automatically figure out some of these without doing a whole lot of work. And the reality is, there is a way. So if we can take a look at our equations here. Now, I graph these on a calculator because that is the most efficient way to do that as far as getting these points on there. In Activity 2, we're looking for what are called horizontal asymptotes and y-intercepts. Horizontal asymptotes are basically if a function goes to infinity or negative infinity, really, really large numbers, what is the function approach? Let's go back to Activity 1 and take a look at some of these graphs. You may have noticed that all of it, well, most of them, A was a very tricky one because the dotted line didn't show up. But most of these graphs do have dotted lines. These dotted lines are what are called horizontal asymptotes. And effectively what's happening here is this graph is going to get really, 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 really close to an output of -3. It doesn't actually get there, but it gets really darn close. Now, this is a tricky piece of the definition. A horizontal asymptote, the graph technically can jump over it, because it's just what the function is approaching as you get towards infinity or negative infinity. We're not really going to worry about that so much in Algebra 1. That's more of a topic for Algebra 2. So for our purposes, they're effectively a wall that we know for sure that we can't go below that -3. That's what the function's approaching. Well, the nice thing is, if we were graphing this with our calculator, we can look at the table and see that the output is getting very, very close to -3 as we move to the left, or move to a more negative input. Never actually gets there, but it gets pretty close. All right, so here we have the graph f of x equals 3 to the x plus 2. In part A, we're asked to find out if the graph is increasing. So if the graph is moving up from the left to the right, it's an increasing function. In graph G, we have this function here, which would be a decreasing function. Now, this is the cool part about this. This goes back to what we did in section 29 when we talked about modeling functions and which one's a growth and which one's a decay. Well, if the values are increasing, we know that's a growth function. If the values are decreasing, we know that's a decay function. It's all related to this number at the base, 3 1/2, or whatever the base happens to be. If the base is bigger than 1, every time we add another piece to it, we're going to be multiplying by a number bigger than 1. The number gets bigger. It's increasing. So this would be an example of an increasing exponential function that is also a growth function. Here's an example of a decay function that happens to be decreasing. That's because b is between 0 and 1. For the second question, we're looking for the y-intercept. Again, the y-intercept is where the graph crosses the y-axis. If we don't have the graph, though, or the means to find it, the quick, easy way to find it is to plug 0 in for x. We know that when we have a y-intercept, x is 0. Plugging 0 into here, into this function, we get 1 plus 2, which would give us 3. Same thing here. When we plug 0 in, we would get 1. Part C, we're asked to find the equation of the horizontal asymptote, looking for where this graph kind of levels off. So right here, at y equals 2, the graph seems to level off. And same thing down here, at y equals -3, the graph levels up. Ignore that there's a little kind of hook at the end here. This graph is just supposed to be flat. Same thing here. It doesn't suddenly jump up at the end. You're getting smaller and smaller. Well, the easy way to find that is just this number right here. 2 and a -3. So our equation for the horizontal asymptote is y equals 2 and y equals -3 for those particular ones. If there is no number there, then the graph has a horizontal asymptote of y equals 0. And then in the closure, we're just kind of connecting it all together. Answer the questions based upon the graph that's given. Find the y-intercept, it's -2. The x-intercept is -1. The equation of the asymptote is y equals -3. This function's decreasing. And is this 0 of the function positive, negative, or 0? The 0 is the x-intercept, so it'd be a negative value, and it happens to be -1. So essentially, we're looking for these 4 or 5 things on the graph. And if we can do that for an exponential function, then we're good to go from this section.